Okay, great. Thank you, everyone. You are in A102, Codecs, Containers, and Protocols, Digital Media Formats for Online Distribution. My name is Matthew Zatmary. I work at Twitch TV. We're going to be going through some basic history of how we got in the state we are today in terms of codecs, containers, protocols. Streaming video really comes from, the modern streaming video really comes from a history of two major disciplines influencing it. Obviously, we have the TV broadcast industry, but recently with the internet becoming a major distribution force, computer science has come in very strong in this industry as well. And because of these two distinct backgrounds, we ended up with a lot of an odd state that we're in where there's a lot of vocabulary disconnects and just some confusion. So in 45 minutes here today, going over lists of codecs and containers and how they work together and everything, it's way ambitious. So instead of trying to cover all of the what and how of all this, I'm going to cover a few specific elements on why some of these things are today, why some protocols or containers are more popular than others, why some things seem more difficult than they should be. Basically, my attempt is try to make some of this stuff a little less intimidating to people who don't do this every single day. So I come from a computer science background, so that's where my perspective is going to be on this. So anyone who has more of a broadcast might disagree with me on a few points here today. But with computer science, when we talk about pretty much everything, we divide it into layers of abstraction. So everything is built on the thing before it. So software is built on an operating system. An operating system is built on a kernel, is built on hardware. And we get higher up the stack or lower down the stack. So everything is built above it or below it. I'm sorry. So in the codec container video world, the lowest layer we're going to be talking about today is the codec. So this is the title page from the H.264 specification. The word codec, for those of you who don't know, it just means coder decoder. It's just kind of those two words scrunched together. So the important thing to note, though, is that codecs are really standards. They're not implementations, they're not physical. They're just a document. They just say how video should, or audio for that matter, should be represented. They're basically, how do we take multidimensional data? In the case of video, we have width and height and time. In audio, we have time and signal. And how do we take that data and represent it in a way that if I give it to you, you can understand it? And by documenting that, that's how we can do that. So now we can have multiple organizations work together off the same basis and be compatible. So again, just for the confusion, we name these things differently. So ISO has what they call it a 14496. There's MPEG-4 Part 10, AVC. These all mean the same thing, and they're all talking about H.264, specifically the H.264 implementation. So this can sometimes cause confusion. I've got the question a lot about, are we using H.264 or are we using X.264? Well, both, because X.264 is an implementation of H.264. So many different companies have different implementations, but they're all of the same standard, so this is just to make them compatible. Another thing that's described in these documents is how to take this data, and once it's encoded, how to serialize it. So Wikipedia definition here, serialization in computer science is the context of data storage. Serialization is the process of translating data, structures, or object state into a format that can be stored, for example, in file or memory buffer, transmitted across the network connection link, and then reconstructed later and in the same or another computer environment. Basically, what this is saying is in computers, everything is one-dimensional. All memory is one-dimensional. It's an ever-increasing length of individual bits. We look at video frames and we see two-dimensional and we see time, but that's all represented in this one-dimensional data structure. So serialization is a way of taking that data and stretching it out over a number of bits, and then those bits can be stored in memory, transmitted over a network, or stored to a disk. So this is from the H.264 specification, and this is one piece of it. It's a very small piece. The specification in and of itself is 790 pages in the last document I have. This is one of those pages. This is something called the sequence parameter set in H.264. This tells the decoder everything it needs to know to start decoding the video frames. So this has information such as the resolution, the profile level. It may encode the frames per second. It has information about what color space we're in. Basically, just everything the encoder needs to know to get going. But this specification, or this particular part of the specification, also shows how to serialize that. If you look down the columns on the right, it says, or right at the very beginning, it says profile IDC, and it says U8. That means the profile IDC value is encoded into 8 bits. And then there's 5 constraint flags, 1 bit each, and then it just continues. So if you take all this data, pack it in the structure, write each piece out using that number of bits, you end up with a packet at the end. And that packet, the decoder knows how to read and parse. So H.264 encodes these packets into something they call NALUs, which are network abstraction layer units. They're really just a packet of variable length. It could be a sequence parameter set, it could be a keyframe, it could be a B-frame, it could be supplementary enhancement info like your subtitle, something along those lines. So these NALUs now we end up with multidimensional again. We have multiple NALUs. So the H.264 specifies a way of getting this into an elementary stream. So we refer to as an elementary stream is that final serialized version of a codec. So H.264 doesn't specify a specific way of doing that, but it does give an optional way. And that's called Annex B, and it's actually specified in Annex B of that document. And all this says is if you use a specific byte sequence, either 3 or 4 bytes of 2 or 3 zeros followed by a 1 byte, and then use that at the start of every network abstraction layer unit, then the player can actually find every single network abstraction layer unit in the stream, and it knows how to decode it. But there's also a second form, which is specified in a separate document, which is the ISO 1449615, called the AVC Decoder Configuration Record. You don't have to remember this. It's also called AVCC or MP4. It's also often referred to as MP4 because this is the format that MP4 files use. And what this does is this is similar, it has the same job as the Annex B, except this takes the parameter sets that the decoder needs to decode the video and kind of sets that aside of the elementary stream and leaves it up to the codec or the container to deliver that as a separate piece. And we'll get back to that in a little bit. So here's an example of a real elementary stream. For those of you who don't know, the image is Lena. This is a standard test image that's been used in computers for testing color reproduction since about 1973. It's been used for decades, very famous. I like this example. I use this as an example on a Stack Overflow question that I answered, and I like this a lot because it's a recognizable image, but once compressed using H.264, it's extremely small. This whole image is only 630 bytes on disk. And this is the complete elementary stream representation over on the left. So you can see what I was talking about. I wish I had a laser pointer. But at the beginning, you can see that start code that I mentioned. You have 0001, and then followed by 67. And that 67, the 7 means this is a sequence parameter set. If you look down on the second line at the end, it's 000, and then it wraps to the third line 1. That's our next start code. 688 is called a picture parameter set. It's part of that extra data. And then a little bit further in the line, you see 001. That's a 3-byte start code, followed by 65. 5 is the keyframe. So the rest of that data is the actual visual video coding layer data, as it's referred to in the specification. If we had an additional frame right there at the bottom, we could just add another start code and then have a 61, 1 being a B frame or a P frame, and just continue the stream indefinitely. Sorry, I moved forward too fast there. So anyway, this shows how to encode video into an elementary stream, but we still have multi-dimensional data because we want to add audio. So when we add audio, we now have 2 infinitely long single-dimensional pieces of information that we need to get down to a second one-dimensional or a new one-dimensional layer. And this is referred to as multiplexing. So another Wikipedia definition here, in telecommunications and computer networks, multiplexing, sometimes contracted to muxing, is a method by which multiple analog message signals or digital data streams are combined into one signal and shared over or sent over a shared medium. So this is really just more serialization. And this is where we get to the separation of the protocols and containers and codecs. So a lot of people might look at an MP4 file and say, oh, this is an MPEG-4 file, and make assumptions about the codec inside. That's just the container. The container does the multiplexing. It also serves several other purposes. It encodes timestamps to make sure those streams are aligned, so you continue lip sync. And it'll oftentimes, in the case of like protocols, have information about retransmission and everything along those lines. But since they actually serve the same purpose, containers and protocols, the lines tend to get blurred a little bit. You end up with things like transport streams, which kind of fall into both camps. As a rule of thumb, I tend to think of protocols as an on-wire representation and containers as an on-disk representation. Protocols often have some sort of intelligent server component, whereas a container might make assumptions about the medium it's stored on, like access times on a hard disk or on a CD-ROM or something along those lines. But like I said, they'll have properties of both sometimes. So I'm going to now that we've covered that, take a quick detour here, and we mentioned muxing. And some of you may have heard the word muxing before, or I'm sure many of you have. But another question I get a lot of is, what's the difference between a transcode and a transmux? So you can use FFmpeg as an example here, and it's very small on my screen, I apologize. So in this example, we're taking a MP4 and just converting it to an FLV. So if we dissect this instruction here, we're saying, hey FFmpeg, take -i input file MP4. So now it knows this is an MP4 container, and it knows how those elementary streams are muxed inside of that MP4 container. We're now saying, I want you to take the video codec libx264 and set that up, because I'm going to encode with it. Take the audio codec libftk AAC, set that up so we can decode with it, or encode with it. I then want you to read the MP4, processing every frame by decoding it, sending it to the correct encoder, and then at the end, I want you to send the output of those two encoders to the FLV muxer, and then finally out to the FLV file on disk. So there's a lot of things going on in this simple command. But as you know, encoding and decoding video, it takes a lot of CPU. So sometimes you'll have an MP4 file that you want in an FLV file, but it's already in H.264 and AAC. You just want to switch containers. That's called a transmux. So FFmpeg uses a special codec type called copy. And this codec type basically says, don't decode, don't encode, just take the elementary stream out of the MP4s, split them into the two elementary streams, the audio stream and the video stream, and send those two streams down to the FLV the muxer and write that out to disk. And this is extremely fast because muxing and demuxing is a pretty light operation. Generally, on a command like this, your bottleneck is going to be the throughput of your network or hard drive. So it's a much more efficient way of processing the streams. So to dive into a little more specific examples here, RTMP. RTMP is what I'm going to use for a protocol example. RTMP is very successful, mostly due to the success of Flash on the internet. RTMP made it very easy for a very long time to get video on the internet, which, as we all know, is a very hard problem. RTMP, though, the name itself is a little interesting because it means real-time messaging protocol. It's not media protocol or video protocol, it's messaging. So this basically is just a method, a document from Adobe. It's not backed by any standards bodies that I'm aware of. But it's just a method that Adobe said, well, you can take, using this protocol, you can take multiple messages and send them from a client to a server. And those messages really could be anything. They're generally referred to as tags in addition to messages. And RTMP takes these tags, multiplexes them, and pushes them over TCP. The multiplexing in RTMP is pretty straightforward. It just takes each tag and it breaks it down into fixed size chunks, and then we'll send a little from the audio frame, a little from the video frame, and try to get those two frames at the destination around the same time. Even though it is generic messaging protocol, there are some standard tag types for audio, video, and script. Script is just their name for metadata. It's part of the Flash scripting background, which is why they refer to it as script. And then if on receive end you take these tags and you save them out to disk in timestamp order, that is actually exactly the format of an FLV file. So RTMP is a protocol for sending FLV, essentially. So we're going to look at the actual format of an FLV tag here. So you can read this this diagram by each row is a byte, and each column would be a bit in that byte. So if we look at the first byte, you can see bits 3 through 7 store what type of tag this is. This is a video tag, an audio tag, or a script tag. There's a data size to say how big this tag is going to be. There's the timestamp. I mentioned that they have to be aligned. You have to be able to play them back in order at the other end at exact moments, otherwise you could lose sync. That's handled through this timestamp. Stream ID is actually not used in the format, even though it's there. Then there's optional headers for sound. So if tag type equals 8, it'll send the stuff in the blue. That'll say, what codec is this? So in this case, MP3 is 2, AAC is 10. I think there's quite a few audio codecs in there. I didn't want to list them all here. But then it also says what's the sound rate, that would be sample rate, channels, things like that. Video, same thing. We have a special video header type. In this case, if it's video, there's a frame type, which would be iframe, pframe. And there's, again, codec, just like in audio. So there's about 16 different codecs in RTMP. Onto VP6 is number 4. Number 7 is AVC. I chose to list those two because they're by far the most common used in RTMP and FLV. AVC, which of course is H.264, is common for obvious reasons. The onto VP6 is quite common because that's what the Flash player itself is able to produce. So if you use Flash to video conference or stream right out of your browser, it's probably using VP6. If it does use H.264, there's an additional header part. And there's this extra byte down there that I have labeled AVC header in green. And this is a byte that says, is this a sequence header or a NALU? I want to point out here, this is odd, because this is a case where Adobe chose to label things very strangely. Sequence header, this goes back to what I was saying about the different elementary stream formats of H.264. This is using that MP4 style, the AVCC style format. And in this case, that packet type, if it was set to 0, would have that extra data, that the decoder needs to initialize itself. I'm not sure why they called that. They called it sequence header because it's sequence parameter set, but technically there's also picture parameter sets in here, so I'm not sure why they chose that name. Also, AVC NALU, this is very deceptive too, because this really should be called an access unit. In H.264, an access unit is a frame, and an access unit can contain multiple NALUs, multiple network abstraction layer units. So they should have called this an AU. I'm pointing this out because, as I was saying, a lot of the confusion in video comes around vocabulary and misuse of vocabulary. And this is in an official document from Adobe misusing the word. So it gets extremely complicated through some of these things. And then, of course, you have the body, which would be the actual payload, would be the extra data or audio data or video data. And then it repeats the size of the tag again. This is theoretically so you can walk through a file backwards. I've never actually seen that done, but that's what it's for. So I'm going to revisit the transcode transmux using what we just talked about. So here's another transcode example. We're going to take an FLV and go out to a TS file this time. Maybe we're going to segment this for HLS a little bit later on. So here's our transcode, and of course, success, runs no problem. But this file, lucky enough, is AVC H.264 AAC, so we're going to try to transmux it. So we run the command, and we get an error. Well, great. So what's the problem here? Well, In this case, you can actually see where it says MPEG-TS. So this means this is from the MPEG-TS muxer, the bit of code in FFmpeg that's actually doing the muxing. It's saying, I can't find a start code. I want a start code. Because transport streams use the former Annex B style format. So it's giving you an error. It's saying, I don't know what this data is. It's probably MP4 style data. Try using this bitstream command. So it's being helpful and telling you what you might be able to do to solve the problem. It turns out in this case it's right, but this is the reason why sometimes when you're doing a command like this, you have to add this extra information that seems like you shouldn't need to. It worked before. It worked when I went from MP4 to FLV, but now it's not working. What's changed? And that's exactly what changed, is that particular bit elementary stream format. So I'm going to talk a little bit about CDNs while we're off on a bit of a tangent. So CDNs historically have provided really good options for streaming servers, for RTMP, for RTP, all the protocols such as that. But they had some disadvantages over like HTTP as its counterpart. Part of those advantages are like the software itself is particularly complex. A lot of the software has to track users individually, so now every user has to be tracked on the server, so now the server requires more RAM, more CPU resources. That software is generally not free, so you have to pay licensing. And just in general, it makes delivery of these formats way more complicated. HTTP has some really interesting properties that would be great if we could take advantage of over these streaming services. So one is, like I said, cheaper hardware, because we don't need the HTTP is stateless. Once a piece of data is delivered, the server can forget about it. It can forget who asked for it. It can forget all that data. It doesn't need to track anything. The software is cheap, like as in free. Adobe, Apache, Nginx, Varnish, very, very good HTTP architecture systems, and they're free and open source. There's also cache efficiency with HTTP. If I request a file from halfway around the world, then it'll take time for me to get it. If I request that file a second time, the edge kept a copy for me, so I don't have to go all the way around the world again. With protocol, some sort of streaming server, there's additional information because you go to the edge and the edge says, I don't know who you are if you want HTTP. So it has to send you all the way back to the origin again. HTTP will just say, oh, I have a copy already. You don't have to go back there. And then, of course, lastly, is just economies of scale. The rest of the internet works on HTTP. Because of that, you could just get these economies of scale. They're building these massive CDNs out to deliver your web pages and your images, and because of that, if we can backbone jump on the bandwagon of that, then we get all that advantages. We get the cheaper delivery of the exact same video. So that's where progressive download came in. The idea was, hey, what if we just take our FLV file and we'll throw it up on an HTTP server and start playing it? Well, that sort of worked. Basically what happens is the file starts downloading, and instead of downloading to your downloads folder, it stores it into a little temporary folder that somewhere deep on your hard drive that you can't see, and then just starts playing that file off of the hard drive. And it works okay. The problem, of course, is you can't play something that hasn't been downloaded yet. You have to wait. And if you want to jump forward, you have to wait until all the things you don't want to watch is downloaded. There is a part of the HTTP 1.1 standard that became popular around 1996. It was actually out prior to that, but there wasn't a lot of support. That does let you say, I want to request a file starting at a certain offset, but that offset is in bytes. So you still need to know at what byte you want to start at. And I showed you the FLV format, and if we just jumped into the middle of a tag, it would look like gibberish. We have to start with, we don't know what frame type it is, tag type it is. We don't know the timestamps. We don't know how to line ourselves in that stream either. So we have to download one tag to know how big the next tag is, to know how big the next tag is. So we can't use the HTTP 1.1 byte ranges to jump around in the file. So people thought of that. And that's why MP4 became popular, because MP4 is an on-disk container. It really had no history of streaming. There's a minor exception to that in the case of hint tracks. But this was really designed as an on-disk format for video. So being on disk, they thought, well, you're going to want to jump around all the time. So they created mechanisms for that built right into the file. MP4 format, also 14.496.12. Its history actually comes from Apple, who invented the MOV QuickTime file format back in '93, and this was extended from that. So the spec goes all the way back to the QTFF. So MP4 is interesting. So MP4 is broken down into individual pieces. Those pieces are called either atoms or boxes. Apple originally called these little chunks atoms, and then ISO renamed them to boxes for some reason. They're hierarchical in nature, so you can have boxes within boxes within boxes, and this is how data can get organized. And of course, as part of that specification is how to take those boxes and serialize them. But there's two important ones that we're going to talk about. First is the MOV, which is movie. It's a weird abbreviation, but that's what it stands for. This contains all the information about the file. This contains all the frame information, the duration of the frames, the timestamps of the frames, how big they are, what their type is. It also contains that extra data in that MP4 format. So it contains everything you need to know to read the rest of the file. So then the rest of the file is stored in just MDAT. It's just data. And this is just raw data. It's without that MOV, it's intelligible. It's literally random. You don't know what's audio, what's video. It's just a dumping ground for data. And the MOV makes reference to that data and tells you how to parse and read that. So when you generate an MP4 file, you need to generate that MOV piece, of course. Now, the problem with that is you can't generate that and serialize that until you know everything there is to know about the file. You need to know about every frame, the size of every frame, the duration of every frame, which means you can't possibly make the MOV box until the file's done, which has two problems. One, live is out the window, because live has an infinite duration, so we can't use this for live. And then number two is, when we do that, at the end of the file, we say, okay, stop encoding. So it takes all the index data it's been collecting, writes it to this MOV, and then sticks it on the end of the file. Well, now we're even worse than we were in FLV, because now we have to download the whole file in order to get to the end, in order to jump back and play the stuff we already downloaded. So the solution to that is something called fast start. So FFmpeg comes with this tool called Fast Start, and all it does is rewrites that file. It takes that bit at the end and writes it back to the beginning. We couldn't possibly know it before, so that's why this has to be a two-step process. You have to encode and then Fast Start. So of course that works. FFmpeg also has a switch, just where you can say move flags Fast Start. I actually think there's a more modern version of the switch. I didn't look it up though. Which this basically says, just like before, create the file and then run fast start, but just do it as one step. But this still does the same thing. It runs two passes on the file. And of course, that works. So that brings us to a little more modern formats, which are fragmented streaming. So we have solutions for everything, but it's across a million different containers and protocols. So fragmented streaming is the latest approach to all this. So fragmented streaming was actually pioneered by a company called Move Networks. So it became popular around 1996. They had limited success. I believe they're owned by DirecTV now. And their technique basically took the video and broke it down into little fragments. This technique, though, became very popular, even though the company itself wasn't so much. It was duplicated by Adobe in the form of HDS, Microsoft at Smooth Streaming, and HLS at Apple. I worked for Move Networks, and we had conversations with all these companies. And 18 months later, they started launching products. So it was a great idea, and it's great that it was able to run with it. So basically, as I said before, it takes this video and breaks it down to little chunks. So it solves the MP4 problem by literally making 2 to 10 to 20, whatever you set, second MP4 files. In the case of HDS and Smooth Streaming, it literally is an extension on top of the MP4 specification. So you still have your MOV box. but it doesn't have the sample data in it. It doesn't have the frame data. This is called your initialization segment. So if you've done much with MSE or Dash, you have that initialization segment. That's where this comes from. That's the history of that. That's your MOV box. But again, it doesn't contain the sample data. So where do we put the sample data now? Basically, they took the sample data and invented a new box type called MOF, which stands for movie fragment. And that contains all the sample data now for that 2-second or 10-second segment. That 10-second segment is stored into an MDAT, just like before, an MP4. And then those are, can be concatenated into a single file for what's called the on-disk format or streamed individually, sometimes with a M4S extension for the on-wire format. So that, as I mentioned before, that enabled live streaming over HTTP. It also gave us the benefit of having smart clients now. So we were able to, now we have dumb servers. Well, if we want to put intelligence in, we can start putting intelligence into the client. So we basically, from this process, got the adaptive streaming for free. The client can now choose which bitrate it wants to handle. And now it just takes the client code to do that, and we can still use all the dumb servers, extremely fast, extremely cheap servers that we've been building out for decades now. And then where we're at today in all this is basically media source extensions. I wanted to bring this up specifically because media source extensions is an extension part of the browser spec where you can actually take these MOF, MDAT formats called fragments and give them right to the browser and it can play them. So we're finally getting out of the plugin system. We're eliminating Flash. Even non-Flash video usually loaded some sort of plugin that was written by the operating system vendor. This is now down at the low-level layers of the browser. This is giving us a lot of places to go with it, and it's abstracting away the high-end stuff, the manifest formats, everything like that. Now we're free to choose what we want to do along those lines. So, for example, Dash has its manifest format that it's promoting, but you could use an alternate manifest format. Dash, of course, is more or less the Microsoft Smooth Streaming binary format with just an XML manifest. I know the Dash people out there are getting really mad at me right now because it's so much more than that. But that's what it is. HDS is similar. That would use an MP4 format. I don't think it's media source extensions compatible. Both Smooth Streaming and Dash should be compatible with media source extensions. Apple, of course, uses the transport stream, which works with media source extensions. Technically, in the spec, it says it's supposed to. The only browser that's implemented that is Safari on Mac, though. So the spec says yes, reality says no. So we're basically going to be the MDAT, the fragmented MP4 streaming with media source extensions is just, that's the future. That's where everything will go. It's barely even the future now. It's pretty much the present. So I was at NAB this year at the Dash IF forum. They said Hulu was sending 80% of its content over Dash now. And really the only reason why it's probably the only reason why it's not 100% is iOS. iOS, we're still stuck with HLS with this transport stream format. Hopefully with iOS 8 coming out, they'll adopt it. If Apple's out there, please. And that's pretty much it for me today. So I have my email here if someone wants to contact me, or we have a couple of minutes for questions, if there's any questions. Yes? Yeah. Oh, well, I don't know what iOS's percent of Hulu, but I know they were.
I just wondering, in general, don't you think Apple is going to just force people to use HLS forever?
No. So Apple's already shown. There's already been cracks in that. Safari on Yosemite supports fragmented MP4 streaming. So nobody knows why Apple does anything Apple does. It was probably pressure from Netflix to get off Silverlight. Even from what I understand, even Microsoft wanted off of Silverlight. And Silverlight was a great way. Silverlight had amazing cross-platform DRM. And until I didn't mention it, but there's an encrypted standard on top of the media source extensions called Common Encryption or EME. And that EME is basically gives you a common way of protecting the data. And then a third party you can do your key exchange and through a third party. So that enabled Netflix to move off of Silverlight, and probably, no one knows anything for sure, of course, but probably the only reason why they were still on Silverlight was Mac, because they could get studio approved DRM on Mac. But yeah, so there's already been showing that Apple is at least starting to adopt some of that. Whether they're going to continue that to iOS or not, I hope so, but we'll see. Yes?
I think last year you mentioned Twitch was converting to HLS at the time.
Yes.
Are you doing Dash already, or is that, you said that's the future?
So yeah, we're still 100% HLS, and because of our architecture, but because we are mostly live content, I don't know what the exact number is, but mostly live. And because we have so many streams that we have to process, tens of thousands concurrently. Also, we run our own CDN backbones, and because of that, we only have two choices. We either have to retransmit the data twice over the backbone, which means our backbone capacity is cut in half if we deliver multiple formats, or we have to transmux at the edge, which means our edges need more CPU, more RAM, blah, blah, blah. So far, we've just been able to get all the players to support HLS. It's tricky to do that sometimes with some of the players really wanting to push Dash. Whether we'll get there someday, I really hope so, but it's really going to be we'll have to figure out something when the time comes. So far, it hasn't been a limiting factor for us, and since iOS is a market we're very interested in, we're not just going to leave that behind, obviously. So that's why we're still strictly iOS, or I'm sorry, HLS. Any other questions? Yes?
So you mentioned your use case is live,
Mm-hmm.
Primarily live. What is that? What does live mean to you? It's similar to my use case. It's live, but I need 700 milliseconds.
Yeah, so our current latency is probably in the 10 to, at the probably absolute best, to maybe 30 at the, probably actually better, probably 20, 25 at the worst, assuming you're not buffering. If you hit buffering events, you might fall a little further behind. That's what we treat. We're trying to improve on that. It's very difficult in HTTP streaming. That's one of the downsides. RTMP, RTP, these are still going to be much more lower latency. But again, as we're saying, the benefits of switching, our biggest problem was actually scale. With the 100 million viewers we have, we just couldn't scale RTMP any further.
Why don't you switch to UDP?
Well, we'd have to have, we have UDP, I love UDP, but you can only use something that the players can play, right? So we'd have to go out and develop all the players that can support that custom stream, right? Well, on iOS, we use the iOS, but yeah, we develop, but in browser, for example. So, in Flash, you can open an HTTP request or a TCP socket, but I don't think you can open a UDP socket in Flash. There's also cross-platform. We're on, Fire TV, we're on, PlayStation, Xbox. There's the the game console. We're on the Vita, Sony Vita handheld. We're on. So. Yeah, we'd have to develop that for all of those platforms. Although it's interesting you brought that up. We were just discussing before we came in here about HTTP 2.0, and Google has some experiments using a protocol called QUIC, which is HTTP 2.0 over UDP, and I'm really hoping they make some progress on that, because that would basically put UDP into the browser, and we'd be able to take advantage of a lot of that at that point. Yes? Well, the joke I always say, there's only two problems with H.265, and that's encoding it and playing it back. Encoding it, we do all our content live. So we have 10,000 plus streamers, concurrent. The top 1% of those might own an Elemental or something that's capable of doing it in real time. But you need what, minimum $15,000, $20,000 in hardware to encode H.265 in real time now. And then on the playback side, it's not there on iOS yet. The iOS 6 actually has a decoder on board, but Apple doesn't let developers use it. They're keeping it to themselves for FaceTime right now. Adoption in web browsers is zero, none whatsoever. Adobe shows no interest in adopting it for the browser. Again, we're years out on H.265, years out. We need it to get it into the hands for playback, and it's just not there yet. That plus hardware upgrade cycle. So even if starting tomorrow, all iOS and Android devices supported H.265 playback, it'll be 2 years for the upgrade cycle to get it into everyone's hands. VP9, same thing for VP9 with one additional restriction is hardware playback. So H.264, 265 being open backed standards, not that VP9 isn't, it's open source, so it's open. But there's a lot of industry, there's a lot of bodies, there's a lot of organizations promoting this format to chip manufacturers. So if VP9, if Google could convince companies to include hardware encoders and decoders into their chip designs, we'll much more likely see adoption that way. But so far, Google actually, no, they shut that down, sorry. No, but yeah, basically they need, it's just hardware support at this point. And you don't want to do it in software because then your phone gets hot in your hand and your battery goes dead in 30 minutes. Yes?
Just to follow up the last two questions. So does years in the future mean years in the future, but inevitable? Or does years in the future mean maybe it's inevitable, maybe something else will happen, maybe it'll just fall by the wayside?
Well, there will definitely be, there's definitely a market for it. So a great market would be, Netflix. Netflix has way more playback than us, but in terms of video coming in, we dwarf it, right? So Netflix can afford to take a movie and spend 3, 4, 5 days, they don't, but they could if they wanted to, encoding it, right? Getting it as small as possible, spending every last bit of resource. Because once that's on the server, it'll be watched 1 million, 2 million times. So if you can save 1%, that's big money over the long run. Same thing with multiple formats. They can do an H.264 version, an H.265 version, and if only 10% of the people can play the H.265 version, yes, let's do it, because we'll save bits, we'll save money that way. For a case like us, where our per channel viewership is lower, we'd say, and the cost of encoding is so much higher that the economics just don't make sense. So is it inevitable? It's here today in extremely limited ways. It will grow. Will it grow? Will it double next year, its usage? Will it triple? Will it go 10%? I'm not sure. Will it ever be just the standard like H.264 is? I don't know, not unless they can speed up encoding drastically, because encoders still, either that or we'll need hardware encoders. We'll just need to start being built into CPUs from day one. Again, now we're in a hardware cycle, and PCs upgrade less frequently than phones, probably 3 or 4 years. So it's, and even then, I don't know. But I hope that answered your question, yes?
What happens when flash goes away, and how do you mitigate future flash?
Well, if you're doing anything today, and you can, I highly recommend media source extensions, because you can just do everything in JavaScript. You don't need any Flash, anything. For encode? Oh, well, encode for streamers. Oh, well, for us, for our use case, our streamers use some dedicated tools. There's one called XSplit and one called OBS. But we still take in RTMP, and we distribute HLS, but anything that'll deliver RTMP will work for us. But there's, we could just switch protocols or something, that works, without the Flash backing. So, any other questions?
WebRTC?
Yeah, so I didn't bring up WebRTC mostly because I don't know enough about it and I'd probably make a fool of myself. It's very interesting to me. It's based on RTP, I believe. It could be interesting. I've seen some demos delivering video with WebRTC. I haven't explored that myself yet, so I can't comment too much because I just don't know. But there could be some potential there. But again, it's a protocol, so now we have to have a server, or it's not HTTP, so CDNs are a problem. And but limited use cases could make a big impact. Okay, is that all? Great, thank you very much.